Welcome to a screencast on more aspects of electron configurations. First of all, let's recall the Electron Hotel, which is sort of an analogy for how electrons are arranged in atoms. And remember that electrons live in energy levels. Here they're represented by floors in a hotel. There's a first energy level, or a first floor, second energy level, or second floor, third energy level, or third floor, and so on. And then the energy levels have sublevels, and electrons in atoms fill in to lowest energy states, going from the first level, then they fill in the second level, then they fill in the third level. And there are specific rules also that electrons follow, such as 2 electrons is the maximum in a room, or what we call an orbital. And electrons that fill into rooms or orbitals that have the same energy, so-called degenerate orbitals, fill into separate rooms until they have to pair up. And remember that electrons have spin, and electrons, 2 electrons sharing an orbital have opposite spin, and electrons that fill into orbitals one at a time have the same direction of spin until they start pairing up. Now, also remember that we have a periodic table that is organized based upon the electron arrangement within atoms. And we can use the periodic table as a guide to remember the ordering so we can get electron configurations. And remember that starting at the top left and reading across to the right and then moving down to the next row, reading left to right, etc., the ordering is 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, followed by 5s, 4d, 5p, and then that's followed by 6s, and then we move down to 4f in the lanthanides, then we go 5d, then 6p, and then 7th row, 7s, 5f, 6d, and we would also have 7p if we kept going here. So let's apply this to an example. Let's do the ground state electron configuration for the element sulfur, which is element with atomic number 16. And remember that the ground state electron configuration is the lowest energy arrangement, and electrons go into shells, subshells, and orbitals. As shown here in the energy level diagram, they fill into 1s, then into 2s, then they fill into 2p, staying in separate rooms until they have to pair up, then 3s, then 3p, until all the electrons are used. So this is the ground state electron configuration of sulfur, and we'd write it 1s2, 2s2, 2p6, 3s2, 3p6. Now, a couple things to note. One is this grouping of electrons, 1s2, 2s2, 2p6, corresponds to the electron arrangement of the noble gas neon. And noble gases have a particularly stable electron arrangement. They're at the end of a row, and we often, as sort of a shorthand way of writing things, will take a noble gas piece of an electron arrangement and represent, instead of writing all of that out, we will simply use the symbol of the element in brackets to represent that part of the electron arrangement. So neon has an electron arrangement of 1s2, 2s2, 2p6. So instead of writing that in the electron configuration, we write neon in brackets, and then afterwards we write the rest of the configuration, which is 3s2, 3p4 in the case of sulfur. This is what's known as a condensed notation, or sometimes called an abbreviated electron configuration or a noble gas configuration. And if you're asked to write out a complete electron configuration, you have to write all of this stuff. But in many cases, what we're interested in is the outer shell electrons. That's where the chemical action is. And so abbreviated or condensed notation is often quite adequate for us. Okay, a couple other things to note. Staying with sulfur, notice that the electron configuration tells us how many electrons are in each subshell, but it doesn't really show what the energy level diagram does, which is how the electrons are arranged in the orbitals and what their spins are like and if they're paired up or not. Now, an electron energy level diagram takes up a fair amount of space, and so what we do sometimes to get across the same idea, convey the same information, is instead of writing the electron energy level diagram vertically, we write it horizontally with increasing energy going from left to right. And then we fill in the electrons, same way we would fill in a vertical energy level diagram. And then this is what's known as orbital notation. And notice this shows all of the electrons reasonably compactly, only takes up a line, and it shows how they are arranged in the orbitals. Now, as with electron configurations, we have a noble gas piece here where all of the subshells are filled up, and so we can combine orbital notation with the condensed or abbreviated notation, and in this case write neon, and then 1s and 3s showing the electrons in those explicitly, and this would be a condensed orbital notation. And then one other thing to note is we can describe or show the orbitals as lines, and we sometimes show the orbitals as boxes. And so this would be an equivalent way of showing things. It shows the electrons kind of in little containers or little hotel rooms or boxes, and so this is sometimes called orbital box notation, or just orbital notation is fine. Now, a couple other things to note. As was alluded to earlier, there's a difference between what are called the valence electrons, which are the electrons in the outer shell, and that's where all the chemistry typically is going on, versus the core electrons, which are all the electrons that are inside, so to speak, the valence electrons. So for sulfur, the valence electrons would be all of those in the third energy level, because that's the outer energy level or outer shell. So they'd be 3s2, 3p6. And the core electrons would be in this case, a noble gas configuration, 1s2, 2s2, 2p6. So what we would say for sulfur is it has a total of 6 valence electrons, 2 here and 4 there. And the valence electron arrangement would be 3s2, 3p4. So let's do an electron configuration for an element a little further down in the periodic table. This is the element bismuth, and we're to write the electron configuration and identify the valence electrons. Here's our periodic table showing the ordering of the subshells, so we'll use that as kind of a guide to help out. And we are looking for the element bismuth. There it is. And we're going to fill in our electron arrangement. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and now we're down into the 4f, which has 14, 5d10, and then 1, 2, 3 electrons in the 6p. So if we write all of this out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and that gets us up to krypton. Then we have 5s2, 4d10, 5p6, and that gets us up to xenon. And then 6s2, 4f14, 5d10, and then 6p3. That would be the complete electron configuration for bismuth. Now the valence electrons are going to be the ones in the outermost electron shell, and the outermost electron shell here is shell 6. So the valence electrons are going to be the 6s2 and the 6p3, and everything else is in an inner shell, and so those are core electrons. So we have a total of 5 valence electrons for bismuth. Now, one other thing to note is xenon is the noble gas that is just preceding bismuth, and so we could also write this in a more condensed form as xenon, and then after that all the rest of it, so this brings us up to xenon, and all the rest of it will be 6s2 for F14, 5d10, 6p3, and that would be the condensed notation. And if you're explicitly asked to write out the complete electron configuration, you have to do this whole thing. If it either says condensed or just write the electron configuration, often the noble gas or condensed shortcut is fine. Now, a couple things to note. First of all, ground state electron configurations are what we have been writing so far. 1s2, 2s2, 2p6, 3s1 is shown here in kind of a cartoon form. 2 electrons in the first shell, 2 plus 6 or 8 electrons in the second shell, and then 1 electron in the third shell. This is the electron arrangement for sodium. This is the ground state or lowest energy arrangement. And now watch what happens here. And maybe you want to see that again. Notice this electron that's in the second energy level is now in the third energy level, not the second. And this is what's known as an excited state. Instead of having 6 electrons in the 2p subshell and 1 electron in the 3s, we have 5 electrons in the 2p and 2 electrons in the 3s. One of the 2p electrons is in a higher energy level than it would normally be in, and that's what's known as an excited state. So the difference between ground state and excited state is at least 1 electron in a higher energy state than it normally would be in. And when that's the case, when we have 1 or more electrons not in the lowest energy state or configuration, then we have what's called an excited state, and an excited state is anything that's not a ground state. So the next question is, we have an electron configuration given, and the question is, what element is this, and do we have a ground or excited state configuration? And there's a couple ways to do this. One is we can look at the electron configuration that's given, see how many total electrons we have, so 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 9 plus 3 gives us 50 electrons, and see what element corresponds to the element that has 50 electrons. And it turns out that's the element tin, Sn. Now, of course, the other thing we can do is look at this electron configuration, or the other thing we kind of have to do, look at this electron configuration and see if it is what we would expect the electron configuration to be for the element tin or Sn. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, up to there, corresponds to the electron arrangement for the element krypton, and that is a lowest energy state. So that would be krypton. And then if we were doing the electron arrangement for tin, we would expect next to be 5s2, 4d10, 5p2. So 5s2, 4d10, 5p2. And we look at this expected ground state electron configuration. We compare it to this given electron configuration and see if they match up. And here we have, instead of 10 electrons in the 4d and 2 electrons in the 5p, we have one of the 4d electrons has, so to speak, moved into the higher energy 5p subshell, and so this would be an excited state, and the reason is because it's not a ground state. Now, there are a couple other things to note, and one of them let's get at by looking at the element copper and predicting its ground state electron configuration. And there's the periodic table, there's the element copper, and the prediction for its ground state electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 if you count. So there's the energy level diagram predicting the electron configuration for copper. And we can write it in noble gas or condensed notation. Argon, the previous noble gas, and then 4s2, 3d9. However, if we actually experimentally determine the electron configuration for copper, and this can be done using something known as photoelectron spectroscopy, it turns out that the actual electron configuration for copper is the argon noble gas, 4s1, 3d10. So instead of the predicted 4s2, 3d9, it's 4s1, 3d10. And this is one of quite a few anomalies in the periodic table, electron configurations that are not exactly what you would predict. And there's too many anomalies or anomalous configurations to expect you to know all of them. And in fact, electron configurations are look-upable on various charts or tables. But you should be able to, even without one of these charts, predict electron configurations in general. And it would be good if you knew a few of the most common anomalies. And the two that will be expected in this class are copper, silver, and gold, all of which have the same basic anomaly. Instead of being something S2, something D9, so for example, instead of being 4S2, 3D9, they are something S1, something D10. So in this case, 4S1, 3D10. And notice that in all cases, we have one electron moved, so to speak, from the S subshell into the D subshell, and it completes the D subshell. So a way to remember is if we have a completed D subshell with only one electron moving, that's actually not an excited state. That's actually a ground state for these anomalous configurations. And then somewhat similarly, two others that might be worth knowing, chromium and molybdenum. And both of these would be predicted to be something S2, something D4, but instead they're S1, D5. So instead of chromium's predicted 4s2, 3d4, it's 4s1, 3d5. And notice this corresponds to a half-filled subshell. So that's again a way to maybe remember that half-filled and completely filled subshells correspond to the anomalies with the cost of one less electron in the S subshell. And a couple more things to be aware of before this screencast is over. Remember that anions are negative ions, and they form when an atom gains electrons. And when electrons are gained or added and an anion is formed, they simply go into the next available orbital that would fill. So for example, if we look at chlorine, the element chlorine is going to have an electron configuration of the neon noble gas core, 3s2, 3p5. And notice that this arrangement is only one electron shy of the noble gas argon. So in a sense, chlorine kind of likes to gain one electron and would kind of like to have the same arrangement as argon. And so that one more electron goes into the next available spot. There's one space left in the 3p subshell. So chlorine, when it makes a chloride ion, will end up having a neon core and then 3s2, 3p6, and it gets a noble gas arrangement, which is pretty stable. And then, of course, notice that neon 3s2, 3p6 is, of course, the same as a complete argon arrangement. Now, on the other hand, cations, positive ions, form when an atom loses electrons. And electrons are lost or removed from the outermost shell. And so here you have to be a little bit careful. You don't want to just, in general, stop a couple electrons or however many electrons short when you determine the electron configuration of a positive ion. The recommendation would be determine the electron configuration of the neutral atom, and then remove the appropriate number of electrons and remove them from the outermost shell. And let's do an example or two. First of all, aluminum. There's the periodic table, and there's aluminum. And aluminum is most likely, when it forms an ion, to lose a few electrons. And in the case of aluminum, it would lose 3 electrons and end up with a neon noble gas arrangement. So neon 3s2 3p1 is the condensed electron arrangement of aluminum. It would like to be, so to speak, the aluminum 3+ ion, and that is simply the neon noble gas core, and the 3s and the 3p electrons are lost. Those are the outermost shell. We remove 3 electrons. And of course, neon is the same as 1s2, 2s2, 2p6. Now what about iron, Fe2+? Well, same kind of idea. There's Fe, and if we predict the electron arrangement for just Fe, we'd have the argon noble gas core, and then 4s2, 3d6. And to make the Fe2+ ion, be kind of careful. Don't just go argon 4s2, 3d4 and stop 2 electrons short, because iron, when it makes an ion, is going to lose its electrons from the outermost shell first, and 4s is an outermost shell, or more outer than 3d, the 4th energy level compared to the 3rd energy level. So even though this is not the opposite order of filling, electrons are removed from 4s before they're removed from 3d, and so the Fe2+ electron configuration will be argon 3d6. The 4s electrons are removed. Now, what if the ion that forms is an Fe3+ ion? Well, in this case, we do the same basic idea, but 3 electrons are going to be removed, and Fe, the neutral atom, is going to have an electron configuration of argon 4s2, 3d6. We saw this already. It's going to need to lose 3 electrons to make the Fe3+ ion, and in this case, as before, electrons are lost from the outer shell first, so that would be the 4s, but that's only 2 electrons. 1 more electron needs to be removed from the atom, and that is removed from the highest energy subshell, and in this case, within the 3rd energy level. So of 3s, 3p, and 3d, 3d is higher in energy, and so the Fe3+ electron configuration will be argon 3d5, because the 4s electrons are removed, and then 1 of the 3d electrons is removed, leaving you with 3d5. And that is it for the More Electron Configurations screencast.